Hi, I'm Tim O'Reilly, and I'm here with Carl Bass, the CEO of Autodesk. Carl, you are in some ways in pole position for this next revolution, where we're dealing all of a sudden with smart stuff, with dumb stuff that's made with smart tools, with this revolution where hardware meets software and even wetware, bio, and you guys are all over this. So you have a unique view of what's coming. Can you talk to me a little bit about what's most important in how you're thinking about this next revolution in technology, what lessons there should be for entrepreneurs, but also, how do you think about what's possible as we go forward? We're just starting to understand what we can do now that we've got so many sensors, we've got so much intelligence in our stuff.
Yeah, I think it's true. I think, people start out by driving, looking at the rear window.
Yeah.
The exact same thing is true in the world of making stuff. I mean, for those of us who think this is funny, we talk about black aluminum. Mm-hmm. So what's black aluminum? It's when you take a part that used to be made out of aluminum and you now make it out of carbon fiber. And all you do is you just make it out of carbon fiber, and you go, that wasn't the point of having that part. The thing was a function it was supposed to perform. It was supposed to be a bracket, it was supposed to be strong, it was supposed to not to deflect. There were some properties you wanted, and it's really the same thing. So the first naive response is to take a new technology and do the old thing with it. It takes a while until you can start reimagining things, and what I see happening is the first thing that you need in this is you need this new tool set, in the software, hardware, materials. But the more important thing and the more difficult thing, obviously, is a new mindset. How are you going to think about this problem differently? How are you going to reimagine what you can do? That's the exciting part.
Yeah, Dale Doherty, the creator of Make Magazine, made a really interesting point in a conversation last night. He said the thing that was so exciting about kids and 3D printers as opposed to adults and 3D printers, he said adults want to make stuff that they've made before, where kids want to make things that they've never seen before.
That is that is an interesting thing.
Yeah, and there's that making generation is going to do some very, very different and interesting things. But back to your black aluminum, that brings up the whole point of different materials have different properties, and therefore you can literally think about how you would redesign for that function.
Yeah, and that's what we've spent a lot of time is giving people tools that allow them to rethink this. One of the things I talked about this morning was this idea of, rather than starting by talking about the geometry of the thing you want to make, is actually using the computer to specify the outcomes you'd like to see. Right. So you specify the behavior of what you want, and then you let the computer generate hundreds or thousands or millions of alternatives to satisfy those requests.
Right, I need to carry this much load, I need to have this kind of braking strain, I need to have, be able to generate this much torque.
It can only fill this volume. So take a simple example. Let's say you're making a bracket for an airplane. And you generally want it as strong and light as possible. So those are the main constraints, but you say you can only fill this envelope, it needs 2 mounting plates, it has 4 mounting holes. Go about doing it and go calculate. And what's really interesting is the answers that you can come up with. Now, part of it, is important, is that I have this fundamental belief that, in the limit, computing is becoming free. That we will have infinite computing. And that for most of the time that you and I have been involved with computers, we've treated it as kind of a scarce resource. It's somewhat precious. But if you look in the limit, it's predictably the price of it is predictably going close to zero.
Right.
And the question is, the profound thing is, okay, what would I do differently if I truly believed it was going to zero? And things like using thousands and thousands or hundreds of thousands of core hours to compute something is a new way of thinking. So, it's the computing equivalent of big data. It's like, just as we saw with big data, and even though it saddened me in some strange way, as trained as a mathematician, it's always saddened me when brute force wins out over elegance. Because you just look and you go, oh shit, damn. I really thought we could have an elegant answer to this, but what really works is brute force. There are brute force approaches to computation that are the same way. But you have to have this belief that it's going to be cheap enough to do it. That if I'm designing a bracket, I can spend 100,000 hours of compute time and get a better answer.
Right, but there are also interesting other ways. It's not just the constraints in materials. You can rethink how will a device work if it can support itself. For example, the Segway was an early example of that, or the one-wheel skateboard, hoverboard that we saw here at Solid. But there's also really an interesting thing, I think, in that sensors allow us to think about workflows differently.
Absolutely.
So for example, if you can measure and manufacture at super high precision, you can assemble without screws or whatever because the pieces fit together so tightly. Or you can, when a really great example that I don't think people think enough about is if you look at something like Uber, it's really enabled by two very, very smart devices that have augmented their respective humans.
Right.
And it allows you to rethink this fundamental service, of hooking people up in real time for transportation. You go, well, what else is like that?
No, I think this idea of sensing the environment and responding to it allows you to do things that we've never designed in that way of response. Actually, I love the other day, I can't remember where it was, but I met these two guys, and they're building a handheld router.
Mm-hmm. Oh yeah,
detective guys.
Elon
and Alec.
I love that
because
thing.
It's the anti-CNC device.
Yeah, exactly.
And so the idea is instead of I'm going to make this more rigid and tighter, and I'm going to build more jigs and fixtures to hold it. I'm just going to draw a line on something, and it's going to follow it. Yeah. And it's all because it has a sensor that can respond.
Yeah, that's right. And little actuators that correct. You kind of have to just follow about that far the line with that much resolution, and it gets it absolutely fine.
But I've liked that for my whole life.
Yeah,
I'm kind of close to it, and something makes it perfect.
I actually got a taste of that years ago. I had the laser eye surgery, and I remember they said, "Don't look away from the laser." I said, "What happens if I look away?" I'm thinking this laser. They said, "Oh, the laser will stop. It'll just take longer." The thing is, you couldn't do laser surgery without this sort of fine computer control that means that if my eye moves, it's fast enough to stop.
Absolutely.
Yeah. And there's so many things like that where this control aspect is coming into play, where the incredible amount of control that we really have now, sensor and feedback loops, allows us to rethink things like that power tool that will always cut straight,
right?
Or the saw that will stop when you touch it.
Exactly. And I think we're getting there. I still think there's more to go because we really haven't imagined that many systems like this. And one of the limitations that's still out there is this idea, is computer vision. And it's always interesting how technologies, that were researched 30 years ago and then almost discarded, turn out to be the critical links. In many of these things, and you're seeing it somewhat with things like self-driving cars or in the Google, the computer vision problem is still a hard problem. And we mostly succeed because we limit the domain in which we look. But at some point, we will reach the point in which we can do it.
Well, it's funny too. You can use it in all kinds of interesting domains. I had a wonderful meeting with Tommy Poggio, who's one of the original computer vision guys, and he was working on a neuroscience problem, and it was basically detecting depression in laboratory rats using computer vision. And it was like, hey, it's like you got to watch these things. In the old days, a grad student sat there and watched the rats. Right?
Exactly.
It's like this is the most boring thing in the world. Looking for how often do they do certain behaviors? It's like, but I never would have thought, oh, whoa. Computer vision, the solution for detecting depression in laboratory rats that have been,
I gave this funny talk at South by, which was, what are we going to do when the robots take our jobs? And in prepping for it, I was trying to think through all the things that robots, or really smart machines, won't be able to do. And one of them is like this thing of identification. Like right now, I'm a very, energy efficient means to recognize a cat. or recognize, we've been trained for, over millions of years. We've gotten really good at a handful of things because biologically it was required. But over the long term, once again, we will brute force our way to being able to do it more effectively.
Well, I have two answers to that question, which comes up a lot. I've been on a task force about the future of the economy, and there's a lot of hand-wringing about the robots are going to take all our jobs, technological obsolescence of human jobs. And I think two things. One is something that Hal Varian said to me that at first seemed very sort of cold and a little odd. He said, if you want to understand the future, look at what rich people do now.
Right.
And I thought, whoa, that's a very, kind of like, googly.
You've been hanging out of Google too long.
Yeah. But when he explained it, it made sense. He said, look, it used to be that a few very rich people had these big brick-like satellite phones, and now we all do. It's like, and you look down the path of, where we're getting to with, we all go out to eat now. It used to be something only rich people did. So as the society gets richer, you do actually see those things move down. So in that regard, one of the things that I think about, what would we do if the machines take all our jobs?
Right. We'll do just what we want to do.
Well, what do rich people do now? They entertain each other and their friends. Right. It's like that. If you look at Downton Abbey or something like that, it's like this picture of this era in which what rich people did was, hey, and we're doing that now. On Facebook. We're entertaining each other. We don't. Sure, we still watch made media. Right. But we're sharing a lot of media, and a lot of our time is spent just on these ephemeral media things that are us entertaining each other. So technology's allowed us to do that.
But what about the question about the unequal distribution? Because that's really the more poignant one.
It is a serious problem, and that's my second answer to what will we do when the robots take all our jobs. It's like we have a lot of stuff that we need to do as a society that we're not getting to.
Right.
There are all these billions of people entering the middle class. They don't want to eat rice anymore,
right?
Or yams, and that's their whole diet. They don't want to eat a better diet. We go, wow, we got to get better at feeding the world. That's a big one. Energy, climate change. Right. Despite all the deniers, it's some serious stuff coming our way, and we better, we're going to have to do all kinds of things to meet that need. So I think there are grand challenges ahead of us that are going to mean that machines and people are going to actually have to be really good. We're going to need those smart machines because we're going to have some really big problems to tackle.
Exactly.
And so I guess I would just say, find stuff that needs doing that's not getting done now, and we got all these new capabilities. Let's figure out how to do it.
Yeah, I totally agree.
Yeah.
I don't think we're going to run out of. I don't think we're going to run out of things to do. Yeah. I think when you narrowly frame the question, no, the smart machines are going to do a lot of what we do today, just like machines do a lot of what we used to do, but we have plenty of other things to do.
But they're also going to let us do things that, formerly took maybe more skill. I mean, I know you do you do woodworking for fun and stuff like that. And, I go, wow, I'd love to have better tools that gave me a jump up.
Exactly. Hey, the tech to you guys. Everybody should have one. They don't all have. We all don't have to start down here.
Yeah, I watch. I'm having some work done in my kitchen right now, and I watch this guy cutting a sheet of plywood. And I think, well, you put it on a table saw, and you push it through. That's how you get a straight line. He's standing there, holding up one corner with one hand, and he's cutting a straight line down the 8-foot sheet of plywood. Does it perfectly. It's like he's been doing it for
exactly.
that famed 10,000 hours.
Exactly.
But I'd love to be able to do, like if I had a sort of a power saw, like, it'd be the future Tactia power saw, I could do that too.
Absolutely.
Because the machine would make me more capable. It's really, human augmentation is a huge part of
our business is making tools. I mean, we realize right away, we make tools, like I always say, like, we can make the perfect piece of software, but it's pretty sterile. It's like a samurai sword without the warrior. Yeah. Something you hang in a museum. A piece of software. A creative piece of software meant to engineer something new. Without an engineer, it is about as sterile. And so.
But it's interesting though. Back to that idea of tools and what you make at Autodesk. Yeah. It really does seem to me that you really are thinking about how those tools have to change. Back to your black aluminum.
Absolutely.
This idea of, for example, building more of the materials and the constraints into the software so that it's able to take that into consideration as you're doing the design. So it's not just, well, I designed this thing visually.
Right.
It
No,
looks
I mean,
great, but no, it's actually not strong enough. It's too strong. It's using twice as much material as it needs to, so it's going to be twice as heavy.
No, we're totally interested in the materials. So lots of investment in plastics and composites, carbon fiber, and understanding how strong and how you orient the fibers and all the details of doing that.
Yeah.
Which I think is an incredibly important part, but it's also then how do you make it?
Yeah.
I mean, one of the big limitations for most of the people who make things in volume, not printing a single thing on your home 3D printer, is can I really make this well?
Yeah.
Can I make something that once it gets into the world serves the customer really well? And it's good design and bad design, and the more information you can move up in the design process, the better you can do that.
Yeah.
The most expensive thing as a manufacturer, and GM's going through it right now, is a recall.
Yeah.
Okay. It's not only the financial damage; it's the reputational damage that comes through, and it's orders of magnitude more expensive to solve a problem than if they had figured out what was wrong early on.
Although it is very interesting as we get our things more infused with software, some of those recalls become software updates.
Absolutely. It's one of the geniuses of the software business.
Yeah.
We don't have any massive recalls. We have updates.
Yeah, I love there was it was a Tesla recall. And
right.
They said, well, update your software.
Exactly. It's exactly true.
Yeah. Yeah. Good. So I want to talk about bio. You guys are making some interesting moves in tooling for bio, which clearly indicates that you think that this is more than just a mechanical engineering future that you're building tools for. Can you talk a little bit about that?
Yeah, I think it's this combination of bio and nano. And nano may be the bridge a little bit, as a very small scale mechanical engineering problem. And as we saw this morning, it's solid. Neil Gershenfeld talked about it, about how to imbue matter, with smarts. And so we got this idea that one of the things that we saw was a bunch of people were starting to use our tools that really weren't designed for bio or nano. And they were having some amount of success, but then we started to talk to them and say, what are you really trying to do? I mean, it's a question I find myself asking all the time.
Yeah.
You ask me what are they really trying to do, and they start telling you about some button or they want this, and go, no, what are you really trying to do? It's like that parable about building the carpenter that comes along and they're building a building, and then one says, I'm building a monument to God, and they're all doing the same activity, but they have a different view of what they're doing. And so I find myself always asking this question: what are you really trying to do? And what I found out is that these people are trying to solve these really big problems, but they were using really primitive tools.
Yeah.
And then we realized that much of what we've learned about design tools in the inert world actually applies to the biological world. Yeah. That some of the same, kind of design patterns that you see in one place actually work over there. And the second thing you see is back to that thing that I was talking about, where if you believe computing is free, there are many ways to solve this problem. So like the one I talked about this morning was this DNA origami.
Yeah.
There are two ways to do it that I know of. One is with grad students and one with as a computer. And the oldest force, the oldest.
There's probably a third one, which is sort of crowdsourcing certain aspects.
Exactly. The oldest form of labor in the university is grad. Right. That was crowdsourcing. That was an early form of crowdsourcing. And instead, we said we could actually compute an answer to this problem. That it's a knowable domain. And so we started doing some things where we said, okay, we can structurally use DNA to put things together. And we just found a class of problems that we were able to do this. And then some of the stuff where I was talking about, specifying the outcome instead of the details, really apply here. That if you can build a model, a computational model, in which you can process stuff, you can start trying out thousands or hundreds of thousands of alternatives. Yeah. And it's all about, in some ways, it's about getting a digital model of the thing, so you can build a digital prototype, then you can test it in the computer, and then you can do what we've usually, for thousands of years done by hand, build and test. Yeah. And instead you do it in the computer.
Yeah. That, by the way, is to me is one of the most important things about so many of the tools today is prototyping. Yeah. And you can go a certain distance with a digital prototype. Yeah. But getting physical prototypes more quickly.
Yeah, physical prototypes still matter hugely.
And that really changes the design process, I think, when you can get a prototype and turn it around as quickly as you can. I mean, we're still not at the point where it's as quick as software, but one of the biggest things in this revolution is you can imagine something and you can make a version of it that lets you see whether your imagination was correct.
Right. Well, in some ways, I mean, tying into the bio, what was the fruit fly?
Yeah.
But a really good prototyping tool. Right? Why did we all have to, go in and, look at the eye color on Drosophila?
Yeah,
I mean, the idea was they had fast generations.
That's a very good point.
I mean, that was one of the first, biological rapid prototyping tools.
That's a great point.